Hello, this is Jonathan Gardner. We're covering the theory of Python, and I think this is part of the Python tutorial, something that you need to learn if you're going to consider yourself a master of Python or expert at it or something. This topic is pretty popular in computer science programs, and for certain languages it gets a lot of attention. Probably some of that attention isn't deserved, but some of it actually is. So recursion. We really can't do recursion until we understand some basic notion of functions and how the if statement works. So if you aren't familiar with those two topics, please review my earlier videos on those. I'll try to put a link in them in the description or something like that. All right, so recursion. What is recursion? Recursion is when you call the same function you are in. So something that looks like this. So you have some function A, and as part of that function A, you call back into itself. Okay, this is recursion. All right, it's a very popular topic in mathematics because so much of mathematics relies on recursion. You know, you can build up the numbers by just adding 1, for instance. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. You just keep adding 1. So you do that over and over again, you can get all the numbers. Okay, and this also includes stuff where if you were to call another function that would call into this first function, or there's like some circular thing where you're going to eventually get back to the same function you're in. That's all recursion. Okay, now recursion can be a nasty business. So there are some rules of the road that you need to follow if you're going to do it right. Okay, number one, depth is not infinite. So I encourage you to write a recursive function that just calls itself over and over again. And you'll see that Python will poop out after about 1,000 cycles. It'll say, hey, I've done this 1,000 times. It doesn't look like we're getting any closer to resolving this function. So I'm just going to raise an exception and hope that that's the right thing to do. Okay, so Python doesn't have infinite recursion depth. Now, some languages don't have infinite. Well, some languages do actually have infinite recursion depth. And they do something that you might have heard of called tail recursion. And what tail recursion is in certain circumstances, for instance, if you're returning the value of a function, what the language will do is move the frame off the stack with the instructions to call another function and then go back to the function that was calling this one. Okay, so in that case, when you're doing tail recursion, there's a C in there, you can go infinitely. So you can build an infinite loop using tail recursion. Python does not do tail recursion, at least not yet. It's probably Python 4 or 5 or 6 or something like that. You're going to see tail recursion. Tail recursion is a very useful thing once you get it. Okay. The other thing that you need to know is there has to be at least 2 branches in your code. Okay. One that calls the function and the other one that stops or returns a value. Okay. And these 2 branches have to be separate. So in your recursive function, if it doesn't eventually resolve to something that doesn't recurse, you're going to run into a problem. By the way, I've spelled return really funny. It's R-E-T-U-R-N. R-E-T-U-R-N. Okay? Another rule of recursion is to avoid it if possible. The reason why you try to avoid it is recursion tends to be very difficult to reason about. It tends to be difficult to debug. There are certain cases when you need it. And the one case when you need it is you need it for trees. And I plan on making an entire video on tree data structures in Python and how to write the recursive functions you need to do depth first or breadth first or whatever it is you want to do to navigate these trees. And in this video here at the end, I'm going to give you a recursive algorithm that actually is a tree search algorithm that doesn't require a structure. I'll show you how that works. So this is pretty much the only case when you need to do recursion. There's a rule of thumb that you might find on the internet. And the rule of thumb is that for every call of the function, if you don't need to call twice, do 2 or more things, then you don't need recursion. You can rewrite this in the form of a while loop, okay? And I haven't covered the while loop. I'm going to cover that pretty much the next video or very soon. So what I'm going to do is give you some recursive functions and I'm going to show you the while version and why the while version is so much better for those particular functions, okay? Trees. Let's talk about trees. No, let's not talk about trees. I just mentioned that trees arise very often in computer programming. We've already seen trees with the abstract syntax tree and describing how Python compiles itself. And that's about all that I can think of for why would we use recursion, basically for this one case. There's some other cases that may arise, but I don't think it's worth bringing attention to them, or it's worth really emphasizing them as prime examples for recursion, because these other cases that I came up with, they're all better handled by other options. Okay. All right, let's go through some examples of recursion. These are contrived examples. These are not things that you would do in practice. There's other better ways to do this, but we're just going to do this so that you understand how recursion works. The first is factorials, right? So I'm going to write a function that calculates factorials. Def factorial. And you're going to pass in a number n. And if that number n is equal to 0, then it's going to return 1. Otherwise, it is going to return n times factorial of n minus 1. Okay? And what the factorial is in mathematics, you have this notation where, like, if you have 5 exclamation point, that means 5 times 4 times 3 times 2 times 1. Okay? So what is going on here is, let's say we called factorial 5. Okay? I'm going to use up all my sticky notes to do this. Okay? So the first call to factorial 5. So factorial 5. Okay, let's walk through the code. So it says n is 5. Okay. Is n equal to 0? No, this is false. So we're not going to follow this branch. We're going to go to the next block here is an else block, and we're going to execute this branch instead. I actually need a return statement here. And this is return 1. My old Perl habits were coming through. Perl returns the last value in the subroutine. Anyway, so else return n times the factorial of n minus 1. So we need to calculate the factorial of n minus 1. So we are going to call factorial, and this time n equals 4. And then the same thing's going to happen because 4 is not equal to 0. It's going to do it again. And this time n equals 3. And then again, n equals 2. And then again, n equals 1. And then finally, I think I'm falling off the screen here, n equals 0. That's the next call. And when n equals 0, it says, yes, this is true. So it's going to return 1. Okay, so this is going to return 1. All right, it's going to return 1. So up here, this guy is going to return 1 times 1, okay, which is 1. This guy is going to return 2 times 1, which is 2. This guy is going to return 3 times 2. I'm going to use asterisk like Python. All right. And then this guy is going to return 4 times 6, because 3 times 2 is 6. And then finally, this guy is going to return 5 times 24. Okay. And then finally, when that function returns, the result is going to be 120. Okay, so that's an example of a simple recursive function. Go ahead and play around with that. And if you want to see what happens when the depth is not infinite problem with Python, go ahead and plug in the factorial for, say, 2000. See what happens. Okay, might take a while to run, but it should eventually poop out and say, I've recursed too many times. Stack depth is too big. Okay, another popular example of the recursive functions is the Fibonacci series. Let's go ahead and use a different color for Fibonacci. This, I don't know what this is, mauve or something like that. They should put the names of the colors on these. They don't. Anyway, it's some nice purple color. So def Fibonacci. Okay, and we're going to get the nth term. Okay, now in mathematics, the Fibonacci series is defined. So the f sub n is equal to f of n minus 1 plus f of n minus 2. So it's a sum of the two previous terms in the series. And then f of 0 is 1, or 0, and f of 1 is 1. So the Fibonacci series starts off with 0 and then 1. And the second f of 2 is going to be 1 plus 0, so it's 1. Let me just kind of write this out over here. So it starts with 0, then it does 1, and then 1 plus 0 is 1, and then 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 3 is 13, and so on. 8 plus 5 is 13, and so on. So the Fibonacci series, we are going to say if n is less than 0, return 0. Okay. If n is equal to 1, return 1. That's a return. And then else return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay, so let's walk through this. Let's see, this is 0, 1, 2, 3, 4, 5, 6, 7. Do I have 7 yellow sticky pads? I do. Let's do it. First call. So we're going to call Fibonacci of 7. Okay, so when we call Fibonacci 7, we get n equals 7 for that call. And it's not 0. It's not less than 0. It should be less than or equal to. Less than or equal to 0. That should be what that is. It's not 1, so we're going to execute this branch, which is return Fibonacci of n minus 1 and Fibonacci of n minus 2. I realized I might be running out of yellow sticky notes here, but let's walk through this really quick. So we have n equals 6, and we're going to call n equals 6 first. That is going to say return Fibonacci of n equals 5 plus n equals 5. And then n equals 5 is going to call down and do n equals 4. 7 is probably a bit overkill. N equals 4 is going to go down and call n equals 3. All through this first branch right now. And then we have n equals 2. And finally we have n equals 1. And when we call it with n equals 1, so Fibonacci of 1 is going to return 1 because n is equal to 1. It's going to return 1. So this 2 is going to return 1 plus n of 0. So we need to make a new frame because it's doing Fibonacci of n minus 1 plus Fibonacci of n minus 2. So we do n equals 0. And what does that return? Well, if n is less than or equal to 0, it returns 0. Let's take the sticky note off. Set it aside. We're going to be using that again. So 1 plus 0. N equals 2 is going to return 1 plus 0. So it's going to go up here to n equals 3. And it's going to say, okay, so we have 1. And now it wants the Fibonacci of n minus 2. The Fibonacci of n minus 2 is, it's going to call n minus 1. N equals 1. And this is going to return 1. Okay, so it's going to be 1 plus 1, which is 2. And now we have n equals 4 has 2 plus Fibonacci of n minus 2. Well, that's Fibonacci of n plus 2. Well, we know that's going to be 1. We've already done that recursion there. So n is 4 is going to give you 2 plus 1, which is going to give you 3. So Fibonacci of n minus 1 for when n is 5 is 3. And the Fibonacci of n minus 2, that's going to be n of 3, which is this call here, which we've already done. So we're not going to repeat that again. So that's 1 plus 1, that's 2. So it's going to say 3 plus 2. All right, and so now n equals 6. We've called it with n equals 5, and we got 5. And we're going to add Fibonacci of n minus 2, which is going to be the n equals 4 case, which is a 3. So that's going to be 3. We're going to turn that, and we're going to get 5 plus 3 is 8, plus n is 7, n minus 2 is 5. So plus this version, which is 5. And so the result is going to be 13. All right. That seems like madness, and it kind of sort of is, okay? Last case, I wanted to talk about Towers of Hanoi. A, it's actually very interesting. B, it's something that you should spend some time thinking about. Okay, so the Tower of Hanoi problem. This is a famous problem. It's used throughout computer science to explain. It's kind of an ideal case for recursion. It's actually a tree walk, but you won't really see it until you know what trees really are and how they really work. So Towers of Hanoi. What the problem or the game is you have 3 pegs, and then you have disks that are of decreasing size. Okay, so like you have 0, 1, 2, 3, and 4. And the goal is to move this entire pyramid over here. The rules are you can only move one disk at a time, and you cannot place a larger disk on a smaller disk, right? So how would you solve this? And the answer is that you do a little bit of recursion in your mind. You say, well, in order to move this entire stack over here, what I need to do first is move this entire stack to the third one, right? And in order to move this entire stack to the third one, I have to move this smaller stack with 3 plates to the middle plate, right? And in order to do that, I have to move these 2 plates over here. And in order to do that, I have to move the smaller plate, the 0 plate, to here. And then I can move that plate over there, and then I move the 0 plate on top, right? So I've moved that top stack. Now I can move this middle stack to here, so the 2 goes here, and same reasoning to bring the 0 and 1 over on top. Okay, so let's write this out in code. The code will look like this. So def, we're going to call it move. To be short, we're going to have the disk number we're trying to move, and then we're going to have the source, where it's at, where it's going to the dest, and then we're going to have a spare, the column that we're going to use for the spare. These are all integers, okay? So we're going to call this the 0, 1, and 2 pegs, okay? And we're going to assume that it starts with the stack like it is, okay? So if the disk is the 0 disk, we can just move that. So we're just going to print, and I'm going to write this out. You won't really know what this does until you've researched the print statement very well. We're going to say move, and then we're going to say disk from the source to the dest. So when we see in the printed output move 0, 0, 1, that means take the 0 disk from the 0 stack and put it on the 1 stack. Okay? If it's not this one, then we need to move an entire tower. And the way we do this is we say move the disk minus 1 from the source to the spare, using the destination as the spare. Okay? And after we've moved, so if we want to move this entire stack of 4 to here, we need to move this stack of 3 to the spare. Okay? After we've done that, then we can move that disk. Okay? So we're going to say move the disk from the source to the dest. Okay? And then after we've moved that disk, then we need to move that stack that we've moved from here to here back on top. So we're going to say move disk minus 1 from the spare to the dest using the source as a spare. Okay? And this will do everything you need to solve the Towers of Hanoi. Okay? So I encourage you to write this code out. Go home and think about this, understand it, and then try this out. Say move, let's say we have only the 2 disks, the 1 disk. So 1 and 0. We want to move this from 0 to 1 using 2 as spare. And what should we see? We should see it's going to print out and say move 0. It's going to move the 0 disk from the source to the spare. So it's going to move 0 to 2. And when it calls that, then it's going to say move the disk from the source to the spare. So you're going to say move 0 from 0 to 2. After that's complete, it's going to print move the 1 disk from the source to the destination. And then finally, when it moves this disk from 2 to 1, it's going to print move the 0 disk from 2 to 1. Okay? And that's what you should see when you move a single disk. And you can map out what happens when you move 2 disks or 3 disks by using a value of 2. And you can try 3, 4, and 5, and you can see if the instructions are indeed correct by playing this game on a piece of paper or with something. You know, I don't have a Tower of Hanoi set that you can borrow, but you can play this game and see if it actually does what you think it does. Guys, that's it for this video. I hope you've enjoyed this. If you have any questions, please ask below. If you have any ideas for recursive functions, or if you're wondering whether you can rewrite a certain recursive function as a while loop or something like that, I'm going to answer any comment you ask. So please ask any questions you have about Python or mathematics or anything like that. I would love to entertain those questions and see if we can maybe even make a new video on the topics you guys come up with. Thanks for your time. Take care, and bye-bye. This video is part of a series on the theory of Python. You can click on the left to see the playlist and on the right to support my channel. Thank you very much for your time.